Hello again. This is Math 2134 coming to you from the College of DuPage, and the title of this lecture is Compound Interest. Remember, you controlled the throttle on this presentation. Compound interest is a natural application of the exponential function to the business world. So let's recall that we had a formula for simple interest. So I is equal to PRT, where I is the interest earned, P is the principal, and that's the rate, the interest rate as a decimal, and T is the time in years. And the units on the rate and the time have to be the same, so R is usually a rate per year, and T is in years. Now the accumulated amount then at the end of T years are the amount is equal to the principal plus the interest, and the interest we found was PRT. So you see we have P in both places, so we can factor P out. We got A is equal to this formula. That is a simple interest rate formula, or the simple interest formula. Now, it is possible though, and that's what compound interest is. Compound interest is they will always give you interest on the interest you already learned if you leave it in the account. And so what happens is, the first year you would just earn simple interest. But the second year, what would happen is you would earn interest on the amount you had at the end of the first year. And in the third year you would earn it on the amount that you had at the end of the second year, and so on and so forth. So if you look at these formulas, you see that at the end of the first year you would have an exponent of 1 over here. At the end of the second year you'd have an exponent of 2. At the end of the third year you'd have an exponent of 3. In general, after T years, you would have an exponent of T. Now, that's assuming that we just compound things annually. In practice, we compound more frequently than just annually. And so what we do is we adjust the interest rate. We take the annual interest rate and we divide it by M, which is the number of compounding periods per year that we have. It's also called a conversion thing. So I is the interest rate that's going to be happening. And then if we do it M times per year, and T is in years, it's going to be MT is how many compounding events that we have. So we'll talk about periods now, not years. So here's the first period, here's the second period, third period, and nth period. Now notice again, what we have is the amount is always A1 is going to be that's raised to the 1. A2 is that raised squared. A3 is that squared, that cubed rather. And A to the n is going to be that's raised to the n. So that gives us to this formula. So what we have is that the amount for compound interest formula, the amount is equal to P times 1 plus R over M whole to the MT. And A is the accumulated amount, P is the initial principal, R is the nominal interest rate per year, M is the number of conversions, and T is the term. Okay, so here we have an example, and find the accumulated amount after 3 years if $1,000 is originally invested at 8% per year, but it's compounded at these different amounts. Well, this is the formula we're going to be using over and over again. So we will be using these numbers, and the only one that's changing in this problem is going to be M. So if M is 1, we get this calculation, and there is our answer. If M is 2, semi-annually, we get this. If M is 4, we will get this. If M is 12, we will get this. And if M is 365, we will get this. So we've summarized that over here. Notice that it does increase the more often compounding happens, but it actually doesn't change by a whole lot. Now, banks, I think, use this for marketing purposes, and it's difficult for some consumers to be able to reconcile which one is the better deal. And for that reason, we talk about having kind of a common way to look at this, and that's called the effective rate. And the effective rate is the simple rate that would produce the same accumulated amount in 1 year as the nominal rate compounded M times a year. And the effective rate is sometimes called a true rate. So we can take our formula then for simple interest. A is equal to P times 1 plus the effective rate as a simple one. And we can set that equal to our amount that we have from the compound thing for 1 year. T is 1. And so now I can solve this for REFF. I cancel the M's and solve for REFF. And I get, this is the formula for the effective rate of interest. And again, this is an important formula that you should be able to apply. And so what we're doing is we're telling out what are the effective interest rates corresponding to 8% compounded all of these times. And so the effective rate then, what really happens is here, the thing that changes is again M, because we're compounding it at different times. So this is the effective rate if it's compounded annually, and that's just 8%. But if we compound twice, we'll get a little more than 8%. Quarterly, a little more than that. And monthly, a little more than that. And eventually, we'll get here. And so you see, we can use that formula. This is the formula that we're using over and over and over again. The government does have Truth in Lending Acts that were passed by Congress because they think people are confused by all of this. And so it is important for banks to publish the effective rate, and this is also known as the annual percentage yield, APY. Now, we can also talk about the concept of present value. So let's return to the compound formula 6, and this was what formula 6 was again over here, which expresses the accumulated amount at the end of T years when the interest is at rate of R is compounded M times a year. So the principle in that formula over here is the present value, and the A is called the future value. In certain instances, an investor may want to determine how much money he or she should invest now at a fixed interest rate to realize a certain sum at a future date. That's why you're interested in the present value. This problem may be solved by expressing P in terms of A. So we go over here to this formula and we just solve for P. That means we divide by the coefficient of P, this number, and when you divide, you get a negative exponent. So this is the formula for the present value. Here's a couple of examples with this, and again, we're going to be using the present value formula, which is shown here. And so we're saying how much money do you have to put in a bank, paying interest at 6% per year, compounded monthly, so that at the end of 3 years you will have $20,000. So you plug those numbers into this formula and you get this amount of money. Okay, you could also think about this for from a loan context as well. The present value of this due in 5 years at an interest rate of 10% per year, compounded quarterly. Again, we're using the same formula 8, which is again is listed up here. We plug in all those numbers and we get $30,000. Now, one question that comes up is, well, gee, that wasn't changing a whole lot, so what happens if you do it over and over and over again? Well, calculus is the study of limits, and the amount that we have is equal to this by a previous formula, and it's just an algebra thing to rewrite this way. But now we can let the number of compounding events go to infinity. So calculus is a study of limits, so this limit is m goes to infinity of this expression. Now, using properties of limits and the fact that the initial principal is a constant, we can get this, and we can continue to work through it, and we can have that this amount, the limit, as n goes to infinity, m goes to infinity, is the same as this expression, and this piece of it is e. So that means the limit as m goes to infinity of this continuously compounding is p e to the rt. And that gives rise to what we call formula 10. This is the formula for continuous compound interest formula. So the amount is equal to p e to the rt. And if we were to solve this formula for p to get the present value, we would have a formula for the present value. P is equal to a, and then this is e to the minus rt, gives us the present value in terms of the future accumulated value for the case of continuous compounding. So let's do some examples of this, and we're going to use, let's see, so we want to find the accumulated amount after 3 years if $1,000 is invested 8% compounded daily, and then continuously. Well, daily we would divide by 365, and we use this formula right here. So we plug in, and we got 365 there. We plug in all of those numbers, and we get this. Now, if we use formula 10, which is over here, the amount is equal to p e to the rt. That is the continuous formula. You get this. Not much difference. It's 3 cents difference. So you see those differ very little, and that's one of the reasons that continuous compounding is something that really is used for quick calculations. It's a very important tool, especially in theoretical work in financial analysis. Okay, so let's do a applied problem. Life isn't a word problem. So you got this investment company owns an office building located in a commercial district, and the market value of the property is given by this equation. V of t is 300,000. That's E. That's the square root of t over 2 as the exponent. And here it tells you that that is dollars, and t is the time in years from the present. And if the expected rate of appreciation is 9% compounded continuously for the next 10 years, find an expression for the present value of the market price of the property valid for the next 10 years, and compute this for a few things. Okay, well, you see, this is the value, but now what we're going to be doing is we're going to be because this is the expression for the present value of the market price of the property. And so what happens is, from the present value equation, this is what we're going to get. And knowing that Vt also has the exponential in, we can substitute that in. It gets a little bit more complicated. But now we have a formula for this. And now what we're going to do is we're going to plug in 7, 8, and 9, and we get these. Now you might notice that this property starts decreasing in value, and so that means that it fluctuates. It increases, but then it decreases. So that means you might want to know when really should we sell it. And later on in this course, we'll be able to solve this problem for a specific time. Now, there's another class of problems, though, is there we were talking about how much. Now we're going to change gears, and we're going to talk about how long will it take for 10,000 to grow to 15,000 if the investment earns an interest rate of 12% per year compounded quarterly. Okay, well, you see here's our formula for the amount, but now what we need to solve for is we need to solve for t. And so to solve for t, and so we start with this expression, and we can simplify it. We're solving for t. But to solve for t, after we simplify it, we have to take the logarithm of each side, and the logarithm is going to give us t down here. And now we can say that 4t is equal to this, so t is equal to the natural log over 4 times the natural log of this. We can plug this into our calculator and get 3.43. So it'll take approximately 3.5 years, 3.4 years, for it to grow from 10,000 to 15,000. Logarithms do matter. And again, problem 8 is a similar kind of thing. Find the interest rate needed for an investment of 10,000 to grow to an amount of 18,000 in 5 years if it's compounded monthly. So this time, these are your numbers, monthly compounding. And this is the equation that we're going to use. But you see, the thing we're solving for is in the exponent. So we plug the numbers in, and we find that this is what we have once we simplify this, and we're working to solve. Okay, so upon simplification, we have this, and actually we're trying to find the interest rate this time. And so we'll take the logarithms of each side. We'll get the 60 there, and we'll have all of that. And now what we're going to do is divide by 60, and then we're going to use the exponential property of the logarithm. So we'll have this, and r over 12 is approximately this. That means r is this, so that is the percent per year. Quite a bit to think about here, really. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now more than ever, take care of yourself and of each other. God bless you all.